Hello, my name is Nico. It's an honor to be here today with you. I'm going to talk about process races and how to detect them. In this room, we all are OS experts, right? So most of you should understand that command. Raise your hand if you ever use that command at least once in your life. Not necessarily with pizza, but pretty much anything, okay? Don't be shy, raise your hand. Okay, good, I'm at the right place. So we're going to do a little quiz here. I want to test your knowledge around this command. You can try it on your laptop. It's okay, you can cheat. You won't be graded. So the question is, how many lines does the psaux grep pizza command outputs? Raise your hand if you think it outputs 0 lines. Okay. Raise your hand if you think it outputs 1 line. Okay, a few hands. Raise your hand if you think it depends. Oh, wow. You guys are smart. Raise your hand if you think it's the answer D. Okay. Well, the correct answer is it depends. And I'm going to explain to you why by showing you what happens in the background. So you're sitting in front of your terminal. You type the command. And the shell is going to fork ps. Then it's going to fork grep. And eventually, grep will execute the execv system call to load the grep binary. Meanwhile, the PS process is going to read the proc command line of grep. So in that situation, the red command line is going to be grep pizza, meaning that we're going to have 1 line of output. But on the other hand, consider the case where the read system call is performed before the execv system call. The red command line is going to be the shell command line, resulting in an empty output. And that was a process race. And more generally, process races occur when multiple processes are trying to access the same resource without proper synchronization. You might think that the PS grep race is not a problem, right? When you type it in terminal, it doesn't really matter. But when it's used in some scripts, it can be problematic. This is a screenshot of a bug report of a real bug of the LICQ chat client. It's due to the px grep race condition. So that's one example of a process race. And we studied how process races are in real systems. Are there many of them? Answer is yes. So we searched for the word race in 6 different bug tracking systems of the popular distributions. We found 9,000 results. 6. We found 9,000 results, and we've sampled 500 of them. Among those 500 samples, we found 109 unique bugs due to process races. And if you were to extrapolate those 500 samples to the 9,000 results, we would be talking about roughly 2,000 bugs due to process races. So yes, process races are numerous. Now, do we even care? What do those bugs do? Like, are they actually really harmful or not? Well, the answer is yes. We studied those bugs, each of those bugs, and found that they cause real system failures, including data loss, such as database corruptions, data being inaccessible, service being unavailable, application hanging, security vulnerabilities. So yeah, most of the bugs we studied fell into that categories. Okay? So process races are numerous and they're dangerous. But now, can we detect them? Turns out, so we looked at the at the different types of races, and this graphic shows the distribution of races in our study. So we can detect thread races, no problem. We can do that. We can do talk-to races. But to detect the general case of process races, well, fell short. So general process races cannot be detected by using existing race detectors. They don't do that. And it's not so surprising because those races involve different programs written in different languages. And so using any kind of static checkers is not going to be an option. Those programs access many different resources, such as unique sockets, signals, IPC mechanisms, they also access system calls whose semantics are a bit obscure in terms of what resources they actually access. You'd be surprised. And also those races often depend on user configuration and specific site configuration. So bottom line, process races are numerous, they're dangerous, so it's a real problem, and we cannot detect them with existing race detectors. So we created RacePro. RacePro is the first generic process race detection framework. It checks deployed system in vivo by recording live execution with a low overhead. It's totally transparent to applications, meaning that it doesn't require you to recompile or relink or change your existing applications. RacePro can even check applications that contains closed source proprietary code. We used RacePro to detect previously known and unknown bugs. I want to introduce you to RacePro's workflow. There's 3 steps. We first record, then we detect and validate. We start by recording live execution in deployed systems. This gives us real execution of real users. And then we get also a very diverse set of software and hardware configurations. This gives us a much better coverage from what the software vendor actually checks and tests with their beta testing sites. The second step is to detect those races. We analyze the log file offline so that RacePro doesn't impact the performance of the deployed system that much. And third, we validate those races by creating a modified execution from the original recording, and then we deterministically replay that modified execution, and we transition to a live execution so that we can check for failures. And if we see that application is doing something weird, then it's a harmful race. Okay? So 3 steps. We record, detect, and validate. So the first thing I want to, I'm going to talk to you about those 3 steps so that you can see how RacePro works. I'm going to start with the recorder. The recorder builds on our previous work on Scribe. It's a lightweight kernel-level recorder. It introduced 2 new concepts, rendezvous points and sync points. Rendezvous points allows us to do partial ordering of system calls so that while still allowing us to do a deterministic replay. And sync points are used to convert asynchronous events to synchronous ones to deterministically replay signals and shared memory. So because the recorder is using a kernel-level approach, it allows to track kernel object accesses. And this is really interesting for us because we're going to use that for race detection. It also allowed to do deterministic replay and transition to live execution. And we use this for validation. The recorder runs on community hardware with a low overhead, especially for multi-cores. This is important because we run this in deployed systems. And we've seen that it has to be transparent to applications because we want to check races in unmodified applications. So the recorder outputs a log file, and I want to give you a sense of what is in a log file. So I'm going to show you snippets of the log file of the PS grep example around the read and the exec-v system calls. So this is how it looks like. On the top, you have the PS snippet, and on the bottom, the grep snippet. On the left, you have the PIDs. I'm going to explain to you the first 4 lines. The first line, so on the first line, we see that PS calls the read system call, and the kernel returns 11 bytes. We also see that PS is accessing a bunch of resources. Those resources have a unique identifier because each resource in the kernel needs to be tracked separately. We might have different files open and all that. You can see that each access has a serial number. A serial number is the, the number of times that a resource has been accessed since we started the recording. So on the first line, we see that PS is grabbing a read log on the file table to map the file descriptor to a file pointer. We see that the file table has been accessed 157 times since we started recording. Then it grabs a write log on the file pointer to update the file location. And then it grabs a read log on that PID abstract resource corresponding to the grab process. Okay? So that's pretty much what a log file contains. It contains other kind of information. But so with that recording, now we want to detect races. Okay? So we do that offline. So to detect races, we could say, for example, annotate manually every system call and try to find the racy ones. But that would be hard because the semantics are often like a bit obscure. Because the way we do the recording, it's very natural for us to use those resource accesses and directly use them. We actually model every system call into load store micro operations. We map the ID of a resource into memory, into abstract memory address. Okay. So I'm going to show you an example to show you how it works. Back to the log file. Okay. So we select every resource accesses. We take only this. Okay. Then for each resource, we're going to sort the accesses by serial numbers so that they are in the right order. Okay. So here, we're going to take the IDs of each resource, and we're going to pretend we're going to map this into an abstract memory address. Okay, so when we take a read log on a resource, for example, 40, it's going to map to a load on a memory address, okay, an abstract memory address 40, like this. Okay, so this is where it's magic. Okay, pay attention. So consider that each process is now a thread. What do we have? Well, we have a simple multi-threaded process. Okay? So basically, we reduce that complicated process trace detection problem into a well-known multi-threaded data race problem. We can apply existing thread race detection algorithms. So by doing so, we would find that those two instructions are racy, okay? And we would conclude that the system call read and execv are racy. Great. So, but RacePro doesn't stop here. It detects other kind of races, such as the wake-up race. A wake-up race occurs when a waiting system call can be woken up by any matching wake-up system calls. To our knowledge, only RacePro can detect those kind of races. Example, say you have a process that is waiting to read data on a pipe. It's blocking. Now you have two writers that comes in, and they're going to write on that pipe with different data. So they're going to wake read. But we don't know which one is going to wake the waiter, right? It can be either one of them. So it's a race. And the reader might get some data from the first writer or the second writer. We don't know. It might be a harmful race. We don't know. Another example is with wait PID. And I'm going to illustrate that example with a PSGrep example. So this is PSGrep. So the shell first reaps the PS child, and then reaps the grep child. Okay. It's a race because this execution could have happened, okay? The shell could have reaped the grep process first and then the PS process. In the PS grep example, this race is not harmful. It doesn't really matter in what order the shell reaps those children. So, which leads us to the third step, validation. So based on all the races we detected, we need to keep only the harmful ones, okay? So we do so by creating a modified execution from based on the original recording that makes the race occur by simply reordering the race's system calls. Okay? But we have a problem here. So if you change your recording in the middle, it's very likely that your replay is going to diverge, because if you change something in the middle, maybe the application is going to do something completely different. And here you can't replay. So we simplify this problem by truncating the log file right after we modify the log file. And then we transition to a live execution, so we don't replay anymore, and thus we don't hit that diverge problem. So basically, we create that log file, okay, and we do a deterministic replay until the modified portion, but we keep replaying the kernel internal state, okay. Then we replay the reordered race system calls, and then we transition to live execution. We can do so because we replay the internal kernel state. If we were to fake system calls around their place, we would not be able to do that. And transitioning to live execution also allows us to run checkers. Checkers are going to watch the execution. The application is going to be able to run freely, and we monitor the behavior of the application. And whether or not it's doing something weird, then we know that it's a harmful race or not. Okay? So I'm going to illustrate the validation with a PS-grep example. So from step 2, from detection, we find out that those two system calls were racy. Okay? Now the question is that race harmful? So we take the original recording, we modify the order of those two system calls, we truncate the log file right after the modification, and then we feed the replayer with that execution. Okay? It's going to do a deterministic replay until the race. Once the race is replayed, we transition to live execution, so the application is going to be able to run freely after that. And we're going to monitor carefully with checkers the execution. Okay? So that concludes the validation step. To summarize, RacePro operates in 3 steps. It records application in deployed system. It detects offline races, and then it validates them. Okay? So I'm going to talk about some results. So it's going to address a few questions. Did we find some bugs? How heavy those interprocess interactions were? And is the validation step really crucial? I mean, is it really useful? And can we really use RacePro in production? Okay. So this table shows you the bugs that RacePro detected. I'm going to explain the one in the middle, for example. So RacePro detected a race where Upstart wasn't waiting for the Samba daemon to create a directory before spawning a network database server. So that's a pretty complex race, and RacePro can detect that. This table shows some characteristics around those bugs. We see that, it shows the number of processes involved in those bugs, the number of system calls and resources. It shows that tens of processes are involved in those races, thousands of system calls and hundreds of resources. Of course, it would be totally unreasonable to approach this problem with a brute force attack. Okay. This table shows the number of detected races, the number of harmful races. So here you can see on the first line that the number of harmful races is 1% of the number of detected races, which means that validation is crucial. We can also see that many of those bugs were detected using built-in default checkers. And for the ones that we had to write a custom checker, it was a simple one-liner. Okay? This graph shows the overhead of the recorder compared to the native execution. We benchmarked a bunch of popular applications, such as Apache and OpenOffice. We measured that the overhead of server applications is less than 3%. For desktop applications, it's less than 15%. So it's totally reasonable to use RacePro in a production environment. To conclude, RacePro is the first generic process race detector. It does it in 3 steps. It records applications, live execution in production systems. It then detects races offline by modeling system calls into load store operations. And it validates those races by replaying a modified execution, then doing a transition to a live execution, and then running checkers on that live execution. We could detect previously known and unknown races, and we confirmed that the recording overhead was low. So I'm going to show you a quick demonstration of the system. So basically we have the PSOX repeats that command, and we're going to record that execution. We can see a bit of the log file to show you like what I'm talking about when I. Okay, so here this is the trace of the exec-v system call we've seen in the talk. So we can see all the resource accesses. We can see some non-deterministic data and all that. So based on that log file, we then find races offline. So this is going to detect races and then validate those races. Let me retry that. I think something was wrong. Find races. Okay, validate. Okay, so RacePro find 2 harmful races. The one I mentioned in the talk, this one, the read and the exec-v race. It also detected another race, but you can think about what it is, and it's explained in the paper as well. So to finish, you can find some more information on our system website. And also I'd like to mention that the record replay engine we use, Scribe, we've open sourced it. So we'd love to build a community around it. You're more than welcome to use it. It's very performant. And I think it could do a lot of things. So thank you. And I will now take your questions.
So I have a quick question. Have you evaluated whether and how much your recording mechanism affects the parallel speed up? Like, do you introduce kind of additional locking in your recording mechanism that might affect parallel speed up during the recording process?
So we so your question is, do we observe any speed up when we record?
Well, it looks like you have some kind of ID assignment mechanism and serial number assignment mechanism. Is that going to introduce additional locking in the deployment run that might affect parallel speed up?
So your question is, do we introduce additional locking?
Yeah. Okay.
So yes. We introduce some locking, for example, when we track shared memory accesses. Some execution that could have happened without a recording actually now cannot happen because we record. But that's not a problem in practice, because if we can run the recorder all the time in production, so those execution paths that could have happened before, well, we can guarantee that it will never happen anymore because we can run the recorder all the time. So yes, but it's not a problem.